Okay, so the recording has started. So let's start our first lecture. Is there anything people want to say? Okay, then we will start. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL PMRF teaching assistant for the course Introduction to Probability Theory and Stochastic Processes. This course is offered by Professor S. Dhamraja. He is a professor in IIT Delhi. So this is a 12-week course actually. Okay. And on every Tuesday from 7 p.m. to 9 p.m., we will be here for online live sessions in which we will discuss about every week questions and the topics covered in the week. So I hope you people have enrolled yourself, and most of you people are also enrolled for the examination. The exam date will be it's 17th of October. Okay, so anyone who would like to enroll himself or herself for the examination, please do. Uh, Let me start with our outlines of the course. You people have already seen all these things in the lecture. If you haven't seen yet, then please watch those lectures. We will follow, we will first discuss about some basic concepts related to covered in the previous week, and then we will solve some numericals based on those topics. Okay. So the outlines of the course is since it is a 12-week course, and in 12 week, uh, from first 1 to 8 week, we will discuss about probability theory, and then from 9th to 12th week, the last 4 lectures, the last 4-week lectures, we will discuss about stochastic processes. Okay, so in overall, what we will discuss in week first is basics of probability. Okay, then in week 2, we will discuss about random variables. Followed by the moments and inequalities. And in week 4, we will discuss about some standard, discrete, and continuous distributions. Okay, so up to this point, we will discuss mainly about univariate. Okay, univariate random variables and all. Okay, and then from week 5, we will go to the higher dimensional random distributions. Like the higher dimensional distribution is there. Then functions of several random variables, we will discuss about the transformation as well, the bivariate transformation mainly. That is the functions of several random variables. Then we will discuss about cross moments. And the last lecture of the probability theory is like limiting distributions. The TF and chi-square distribution, the exact sampling distribution, it is also known as. Okay, so these are the topics we will discuss in the probability theory. In week 9, we will start with the introduction to stochastic processes. Then we will discuss about discrete time, Markov chain, and then in week 11, we will discuss about continuous time Markov chain. And at last, simple OVM. In models. Okay. Is there anyone who want to say anything? Then you may directly ask here. Okay. Is there anyone who want to ask anything or have any doubts related to anything? Then please ask now. Anyone? Am I audible? Na?
Yes, sir.
Okay. And the screen is visible too, perhaps?
Yes.
Okay, then let's start. If people have no questions, let's start. You people have already know some books. Yeah, thank you. Okay. So week 1, we will discuss about basics of probability. Uh, are you want to say anything, Satvik?
No, sir. No, sir.
Okay. Okay, then the first week we will discuss about basics of probability. Okay. In basics of probability, we will discuss about random experiments, samples, events, definitions of probability, and then probability space. Then we will discuss about conditional probability, the independence of event, the disjoint events or mutually exclusive and exhaustive events, then multiplication rule, total law of probability, and at last Bayes theorem, which is also a special form of conditional probability. Okay, so I'm not going to write those things. Let's start with random experiment. Okay. At any point of time, if you people like get confused related to any question, please ask directly. Okay. At the same point, like what is random experiment? Okay. So random experiment is like an experiment is said to be random experiment. Okay. If its result cannot be determined beforehand. Okay. Cannot be known or determined beforehand. It's like when we will toss a coin. Okay. Suppose we'll toss a coin. And in that case, you don't know whether either head will appear or tail will appear. Okay. You don't know at every trial. At every trial, you have some kind of information that either head will occur or tail will occur, but you do not know which face comes upward. Okay. So this is a kind of random experiment. In the similar way, rolling a die and it comes out to be 1, 2, 3, 4, 5, and 6. A standard die contains 6 faces. Okay. So rolling a die contains either 1, 2, 3, 4, 5 up to 6. Or suppose we draw a random card from a deck of cards. a card is drawn from a deck of cards. Okay. So a deck of card has a fixed distribution actually. Okay, it has 52 total number of cards in which 26 are red in color and 20 not red, like red colors, and 26 are black. Then there are lots of distribution. We will discuss the distribution of cards as well. Okay, so these are kind of random experiment. Okay, you don't know what like event is going to happen, but you have a sample or a collection of events. Okay, so those collection of outputs are called actually a sample space. Sample space is what? When we perform a random experiment, then it is defined as the collection of all possible outcomes or results. Okay, collection of all possible results, okay, of a random experiment is called sample space. Okay, like when we roll a die, then in that case the possibility will be either 1 or 2 or 3 or 4 or 5 or 6. So a collection, this collection is called a sample space, which is usually denoted as either omega or capital letters like S, capital S or something. Okay, so usually we will use the letter omega. Okay, then there is a field. Okay, there is a sigma field, or it is also known as sigma algebra. Okay, sigma algebra is like something, a collection. Suppose a collection f of subsets of omega. Omega is the our sample space. Okay, a collection f of subsets of omega is called sigma field or sigma algebra if over the sample space omega, if it follows three basic properties. Okay, if it follows, like the first one is like suppose this, the sample space should included in the collection as well. Okay, it contains in F. Second is like if any subset A belongs to the collection F, this implies the complement of this should also be belongs to the same collection or subset F. Okay, and the third one is like the arbitrary union. Suppose if like A1, A2 up to a sequence of the random events, it belongs to the collection F. This implies the arbitrary union of these should also belongs to the same collection F. If these three condition is satisfied, then we say that this F is nothing but a sigma field or sigma algebra. Okay, and from there, actually we will define something like okay, you people have know perhaps relate the set theory. Okay, so it is similar kind of set theory. Let me take one example. The example is like suppose we toss a coin. Okay, then in that case our sample space will be either head or tail. Okay, so what we are going to do is we create a constructors collection over this sigma field, sorry, this sample space omega. which is nothing but our power set actually. We will discuss what is power set. So it is phi, it is the single element head, it is the single element head, and the whole sample space. Okay, so this is our power set actually. Anyone know what is power set? Anyone?
Yes, sir.
Uh, can you tell me what is power set?
The collection of set of collection of all subset of sample
Yes, set of
space.
yes, yes, set of all subsets.
So,
Okay,
all
suppose we are
subsets. Yes,
given
sir.
yes, yes, uh, the set constructed by and including all the subset of a set is called the power set of that set. So here this is the power set. Okay. Also we can also okay. Let me first define this. Okay, here you can see that this F is actually sigma field. How we can say that? We can take anywhere, like you can take any elements. Okay, the first, the omega, the sample space itself belong to the this F. Okay, here you can see that. Here you can see that. So that is the first condition is satisfied. The second condition is like what? If any element, like any subset, any collection A belongs to F, then its complement also belongs to F. Okay. So you take A equal to 5, then the complement of A equal to omega, which is there. If you take A equal to omega, then its complement is 5, which is there. If you take A equal to head, then its complement is 10, okay, which is also there. So that means all the second condition is satisfied too. And the third condition is again, you can take A equal to 5 and like A1 equal to 5 and A2 equal to H. In that case, like the union of phi and H comes out to be H, which is also there in F. So that means all the three condition is satisfied. Okay. Suppose you can take A1 equal to head, A2 equal to tail, then their union will be head tail, which is the nothing but the sample space also there. Okay. So that means what? All the three condition is satisfied by this F. That means this is nothing but it is a sigma field or sigma algebra. Okay. Also, let me write one more. Suppose what I'm going to take is the null space and the sample space only. Okay. This is also like a sigma field. Okay. But this is the smallest, which is also known as a trivial sigma. Trivial. Okay. This is the trivial sigma field, which is nothing but the smallest as well. And the largest sigma field or sigma algebra is nothing but our power set. Okay, the power set contains all the subsets of like suppose omega, here omega is the set. Okay, then all the subset of omega, that collection is known as the power set. Okay, so undoubtedly this will be the largest sigma. So that means a set has more than one sigma field. Okay, it is how you will create. So this is the case. Also, you can like suppose what if I'm going to take this as a sample space, then in that case, the total number of subset will be 2 to the power n, that is 2 to the power 3, comes out to be 8. So that means this omega has 8 subsets. Okay, so the power set of omega contains 8 subsets. So all the collection of those 8 subsets comes out to be the largest sigma field. Okay, and also there are other sigma field can be constructed which is less than 8 number of elements. Okay, like let me create one. The trivial one, obviously, this one. The phi will be there. The omega will be there. Obviously, if you can take A, then its complement is actually B and C. So this is also F1 is also a sigma field or sigma algebra. You can check phi is there. Take any value. Okay. The first condition is like this. No? First condition is there is the whole space must included in F1 here. So that means first condition is satisfied. For second, take any value as A. Okay, here take any value. Second condition is any value as A. In that case, its complement will be if you take A equal to this, then its complement is BC. If you take A equal to this, then its complement is pi. If you take A equal to BC, then its complement is A. So that means the complement is also there. And the third is you can take any 1, 2, 3, or 4. It overall the union comes out to be the whole sample space which is there. Okay. So that means all the three conditions as satisfied by this F1 set, the collection F1. So it is nothing but our sigma algebra as well. Okay. So this is how you will define the sigma field of sigma algebra. Okay. These are going to be used, okay, in the further classes actually. So now we will define the definition of probability. Okay. Up to this point, if you people have any doubt, please ask. Okay. Okay, so the probability has mainly three definitions. Okay, the first one is the classical definition, which is also called mathematical definition. The second one is empirical definition, which is also known as statistical definition. And the third, which is the latest one, is the axiomatic definition, which is given by a Russian mathematician Kolmogorov. Okay, so let me start with the axiomatic definition. Okay, okay, let me start with the classical one. In classical definition, actually, we are given two or three conditions, like the elements are equally likely. Equally likely. What is the meaning of equally likely events? Equally likely events are those events which have equal probability, which has equal occurrence of probability. Sorry, which has equal probability of occurrence. Okay, so like when we roll a die, okay, then in that case, coming out one, the probability of getting two, the probability of getting three, four have all equal probability. Okay, and the collection must be exhaustive. Okay, so what is exhaustive events? So exhaustive events are those events whose unions comes out to be the sample. Okay, so in classical definition, the probability of any event, suppose E, is defined as the number of favorable cases upon total number of cases. So this ratio gives the classical definition of probability. Obviously, the favorable case is either equal to the total exhaustive cases or the less than that. So overall, the probability of any event lies within 0 to 1, including both. If the probability comes out to be 0, it is said to be the impossible events. And when it comes out to be 1, it is sure events or certain events. Okay. Usually we will get probability which is lie within 0 to 1. Okay, then there is mathematical definition is also there. Sorry, statistical definition is also there. So which is nothing but we will take a unit, because when we have large number of suppose denominator is infinity, then in that case we need to use limit concept so that we can solve this probability value. Okay, so this is nothing but in statistical definition, suppose the probability of any event is be like, suppose we take unit n tends to infinity m by n. Here m is obviously nothing but the favorable cases and n is our total number of cases. Okay. So for large n, we can use this. Okay. The limit is only used so that we can solve this value. Okay. The main definition which we will discuss here is axiomatic definition of probability. Okay, this is given by Kolmogorov. Okay, so what it says is, let we have a sample space omega, and this cursive F be a sigma field or sigma algebra over the sample space omega. Then we define a function, okay, a real valued function. Then the real valued set function P, capital P, okay, on this collection F, that is fine. Satisfying the following three axioms. That's why it is called axiomatic definition of probability. Okay, satisfying these three axioms. The first one is like, for any element A, which is subset of omega, obviously, for any A, it is always greater than or equal to zero. That is non-negativity. Okay, for all A belongs to this collection. Okay, the second condition is like, the probability of the sample space comes out to be 1. And the third is like, if A1, A2, dot dot, any arbitrary values are mutually exclusive events. Okay, suppose these are mutually exclusive events, mutually exclusive, that is disjoint events. F, then the probability of arbitrary union of AI equal to the summation of their individual probability. If these are mutually exclusive, okay, that is they are disjoint, in that case the probability of union of AI comes out to be summation of individual probability. Okay, so these three conditions must satisfy. Then this P function is called the probability function or probability measure, sometimes we say. Okay, so this P is called probability function, and the triplet, which is the sample space omega, the collection from those sample space, which is nothing but the subsets of those sample space F, and this P. This is called the probability space. Okay, so this is called probability space. Is there any problem up to this point? Anyone?
No, sir.
Okay, then let's define one function, one probability function. Okay, let's define one probability function. Suppose we are taking omega as like 0, 1, 2, and up to infinite. Okay, so for okay, let's define a algebra. Okay, sigma field or sigma algebra. Okay, and I'm not going to write all the values because there are lots of values, infinite number of values. So what I'm going to take is the largest sigma field. The largest sigma field over omega, which is nothing but the power set. Okay, so we are considering the power set, which is also denoted as like this. Okay, so our sigma field will be like the power set. Okay, Okay, let me write here power so that we're not getting confused with the probability function. Okay, so let's define a function p, which is one upon 2 to the power omega plus 1. Here, omega is the elements belonging to the sample space. Okay, so this is our definition of probability. Okay, so now what we need to check is this p function follows all the three conditions. So the first condition is what? For any value related to, sorry, for any elements or any sub collection related to f, it always must be greater than or equal to 0. So here what? Here the p function is like 1 by 2 to the power omega plus 1. And the value of omega comes out to be 0 to so on. So if we take the value of omega is equal to 0, then it comes out to be 1 by 2. If 1, it's 1 by 4 and so on. So in every cases, it always either greater than 0 or equal to 0 for large value of omega. So that means the first condition is satisfied. Now the second condition is what? The overall, the whole space comes out to be 1. So if you remember, you will find that this is nothing but a convergent series actually. What we will get for omega equal to 0, we will get 1 by 2, then 1 by 4, then 1 by 8, then 1 by 16 and so on. So this is a convergent sequence actually and converging to the point, nothing but 1. Okay. The summation converges to 1 and the last value comes out to be obviously 0. Okay. So this is the second condition which holds. That is the probability that the whole sample space comes out to be 1. Now the third is we can take any values. Okay. Uh, here and you will find if these are like already we can see that the values are 0, 1, 2, 3, 4. So these are mutually exclusive. Then you can take any random unions, okay, and you will find the probability must be equal to the 1 by like their summation. Okay, the probability of the union of those number of events comes out to be the summation of their individual probability. So that means all the three condition is going to be satisfied with this p function actually. Okay. So this p function is nothing but a varied probability function or probability measure. So this implies what? This implies this omega, this f, the largest sigma field over omega, and this p function is nothing but a probability space. Okay. So in the same manner, you can define any other functional form like 1 by 2. You can take any other convergence series which is going to follow all these three conditions. Then you say that those are also a probability function or probability means. Okay. So up to this point, is there any question? Okay. So we have lots of properties related to these these probability measures or probability functions. Okay. So let me write some properties here. So for example, we have given like omega f, the sigma field, and the probability function is our probability space. Okay. Then what we are going to do is we will first know the probability of the null space. The probability of the null space comes out to be 0. Okay, these are some properties. If A and B belongs to, like we are given if A and B belongs to this and A intersection B comes out to be 5. That means it is mutually disjoint. Okay. Then in that case, probability of A union B comes out to be probability of A plus probability of B because there is no intersection terms available there. Okay. Also, like for any A belongs to this, the probability of their complement comes out to be 1 minus probability of the event A. Okay. You people have mostly every property you people know. Okay. Maybe one or two. Also, like we are two events, A and B belongs to, and then the addition law of probability is what? A union B comes out to be like probability of A plus probability of B minus probability of A intersection B. These are the only properties. Also, probability of any event A is always, okay, let me write in this manner. Probability of any event comes out to be lie within 0 to 1, including both. Okay. Then we have two more properties. The first is let A and be an increasing sequence of elements in F. Okay. It is an increasing sequence. So that means what? That means AN belongs to like F and AN. It is, since it is an increasing sequence, that means AN must contain in AN plus 1. Okay. For all N belongs to so on. So in that case, probability of limit of AN, this comes out to be limit of probability of AN, where limit n tends to infinity, AN is nothing but arbitrary union of these sequence AN. Okay, so this property is also one of the property. In a similar manner, suppose we have like a decreasing sequence of elements, then in that case we have like suppose we are this and AN must contain AN plus 1. So it is nothing but decreasing sequence. Okay. So in that case, again, probability of limit n tends to infinity, AN equals limit n tends to infinity, probability of AN, where limit n tends to this AN is arbitrary intersection. The first one is union when it is increasing, and when it is decreasing, then it is arbitrary intersection. Okay, so these are only the changes. Otherwise, all the like statements are kind of similar. Only the union and intersection will be changed. Okay, so these are some of the properties of the probability function. Okay, now we have discussed about the classical definition as well. So it's conditional. Okay, now we come to the conditional. So in conditional probability, what we are actually doing is in conditional probability, we make some conditions. We are like we have some more information actually kind of thing. Okay. So we impose some more condition, and on the basis of those condition, we modify the sample space. Okay. So that's why since we modify the sample space based on those conditions imposed, so the probability will be changed. Okay. So the main formula is actually you people have already known. Okay, the probability. Suppose we are given two events. The probability of event B when it is given that the probability A, sorry, the event A has already happened. This is what probability of B given A. That means we need to calculate the probability of event B when we know that the event A has already occurred. Is denoted by probability of B given A, which is defined as probability of A intersection B and the given condition divided by the probability of. Okay. In a similar manner, suppose we can write A given B. So again, probability of A intersection B divided by probability of B. Okay. You know that na, the A intersection B equals B intersection A because the intersection is commutative in nature actually. Okay. So this is the conditional probability. Okay. Also, from here, we have one more. It's independent events. Okay. Independent events are, suppose we are given two events, A and B, for example. Okay. So two events A and B are said to be independent if and only if condition. That is necessary and sufficient condition. Okay. If and only if these, the probability of the intersection of these events must be equal to the product of their individual probability. Okay. The probability of A intersection B equals probability of A into probability of B. Then we can say that the event A and B are independent. Okay. What if we have more than two events? Okay. So in that case, we are going to discuss two different kind of independent event. The one is the pairwise independent event, and the second is the mutually independent. Okay. So pairwise independent event, suppose we are given like a sequence, okay, A1, A2, A3, A4, and so on. Suppose we are given those. Then we say that those AIs and AJ, the probability of AI intersection AJ comes out to be probability of AI into probability of AJ, the product of their individual probability for all I is not equal to J. Okay, that is for every possible collection of I is not equal to J. If this condition holds, then we say that the AIs are pairwise independent. Okay, any two like even from those sequence must satisfy this condition. Then it is said to be pairwise independent. And if suppose we have mutually independent as well, mutually independent is like suppose we have again the sequence AIs, okay, for I from 1 to infinity is said to be mutually independent if and only if the probability of it's like A1 intersection A2 intersection AK or any sub collection from those like sequence, any sub collection from those sequence. Okay. So suppose I'm taking up to K, this must equals their individual probability, the product of their individual. If this condition holds, then we say that it is mutually independent. Okay. So these are two different things. Okay. So it may be pairwise independent, it may be mutually independent. Okay. So we have one example actually. This is already discussed in like the lecture, but I'm just writing here. Suppose we are given the omega is 1, 2, 3, and 4. Okay. This is the sample space, for example. Okay. And we define the events A, it's like 1, 2. The event B, it's like 1, 3. The event C, it's like 1, 4. Okay. And obviously, we take equally likely events. That means the probability of the any omega comes out to be 1 by 4 for all omega equal to 1, 2, 3, and 4. Okay. That means probability of getting 1, getting 2, getting 3, and getting 4 have equal probability. That is, these are equally likely events. So here you can see that now probability of A is like 1 by 2, probability of B is 1 by 2, probability of C is 1 by 2. And then like probability of A is like 2 by 4, that is 1 by 2, which is probability of B, which is probability of C. Okay. Now, what is A intersection B? A intersection B comes out to be 1 actually. B intersection C also comes out to be 1, and A intersection C also comes out to be 1. Okay. Okay. Now the probability of A intersection B is what? It's 1 divided by 4, which is what? Which is probability of A into probability of B, which is like 1 by 2 into 1 by 2 comes out to be 1 by 4. So that means what? That means probability of A intersection B equals probability of A into probability of B. So that means this condition is satisfied for the events A and B. So we can claim that events A and B are pairwise independent. Similarly, when we will check for B and C events, we will also find that event B and event C are pairwise independent, and for the event A and event C as well. So that means what? That means events A, B, and C are pairwise independent. Okay. Now we will check whether it is mutually independent. So obviously it's A intersection B intersection C again comes out to be 1. And the probability of A intersection B intersection C equal to 1 by 4 because the element has 4 elements. Sorry, the sample space has 4 elements and in table only 1 elements. So the probability of A into probability of B into probability of C comes out to be it's 1 by 2 into 1 by 2 into 1 by 2, which is 1 by 8, which is not equal to 1 by 4. So that means what? The events A, B, and C are pairwise independent, but it is not mutually independent. Okay, so these kind of cases can also be. Okay, any problem up to this point? Okay, so we have some more properties related to like conditional distribution. The first is like the conditional distribution. Sorry, the conditional probability is also a valid probability. Okay, it is also a probability measure over the same sample space omega. Okay, so also the probability of the event given the same event is nothing but comes out to be 1. Okay, or if A intersection B comes out to be 5, then probability of B given A is comes out to be 0 because in the numerator term we have probability of A intersection B, and here A intersection B equal to 5. So that means what? The probability of the phi function comes out to be 0. So numerator term will be 0. So the probability of the conditional distribution, sorry, conditional probability comes out to be 0. Again, there is uh, one rule actually, multiplication rule. Okay. Multiplication rule is there. What it said? It said if A1, A2, AN belongs to the field F with there is one condition actually. The condition is like probability of A1 intersection A2 intersection A n minus 1. Okay, 1 less n minus 1. This must be greater than 0. That means it is a possible values. Okay, greater, not is impossible event. It is a possible event. Okay, then not equal to, here it's not equal to, it comes is greater than 0, then in that case the multiplication rule said the probability of A1 intersection A2 intersection AN, this comes out to be probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2 into probability of A4 given A1 intersection A2 intersection A3 and so on to probability of AN given probability A1 intersection A2 intersection a n minus 1. Now you can understand why we have considered this case. This condition is taken because here this term a given b. So that means the given condition comes in the denominator part. Okay. So probability of a1 intersection a2 intersection a n minus 1 must be greater than 0 so that the probability is defined. Okay. So if it comes out to be 0 in that case, it is undefined. So that's why. And this rule is called actually the multiplication. Okay. And there is two more things only to discuss. The second one is total law of probability. So the total law of probability is something like, suppose we are given A1, A2 up to AN sequence, okay, which contained in F, obviously. Then if AI and AJ are disjoint, okay, suppose we are given AI intersection AJ is pi, okay, or all I is not equal to J, okay, and union of AI, that is arbitrary union, okay, arbitrary union of AI comes out to be this. This actually, this condition is called exhaustive that we have discussed now. Exhaustive events. That means all the collection of all those events whose union comes out to be the sample space are called exhaustive events. Okay. So these events are exhaustive events. Okay. Then for any other event B, the probability of the event B comes out to be the summation over probability of AI into probability of B given AI. Provided, since it is conditional, so always write this, provided probability of AI, which will come in the denominator part, must be greater than. Okay. So this rule is called total law of probability. Okay. And this term comes out to be in the denominator part in the Bayes theorem. Okay. So the next and the last topic is our Bayes theorem. Everyone heard about this, na? Bayes theorem. Okay. So what Bayes theorem says? For any event B with probability of B is greater than. So probability of any event AI given B is nothing. The probability of AI into probability of B given AI for ith event. Okay. And the denominator part will be summation probability of AJ into probability of B given AJ. So the denominator part is nothing but this part only, the above one. Okay. So which is our like the total law, total probability. Okay. Which is the total probability. Actually, there is one more thing. This event B for in total law probability, uh, these AIs are like kind of like kind of events. Okay, this event B is actually likelihood event. Okay, this which is associated with all AIs. Okay, we will solve this and then you will understand why I'm telling this. Okay, so here AIs are we can also say these are the prior information. So that's why it is also called prior probability. Okay. And this B is our probability associated with all those prior information. So sometimes some books refer this as likelihood probability. Okay. Or likelihood conditions. And the this probability AI is given B is nothing but our posterior probability. Okay. So this comes out to be the Bayes theorem. Up to this point, anyone have any doubt? Then please ask. If not, then we will solve some numericals from here onward. Any question? No. Okay, then we will solve some numericals from there. Am I still audible? Na? Anyone?
Yes, sir. Yes.
Okay. 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 So from here, like we will solve assignment question. So what we are given, let I'll expect that you people also solve the numericals. Okay. So the question is like let omega f p be a probability space. Let A be an event, A be any kind of event. Okay. Then we need to calculate what is the probability of A union A complement. Anyone who want to say the answer or discuss the question, he or she may directly say it. Okay. Okay, so what we are given? We are given a probability function, sorry, probability space omega fp. So that means what? The function p holds all the properties that we have discussed above. Okay, the omega, well-defined collection of all possible outcomes of the random experiment, and f is nothing but the collection of all those subsets. Okay, for that this p function is defined. Okay, so this is a probability space. A be any event. I'm not talking about any specific kind of event. A be any event. Then what is the probability that A union A complement? Okay, so that's a very basic question actually. In set theory, we know that na, since we know that A union A complement comes out to be our sample space. Okay, the A union A complement comes out to be our sample space. The first condition. The second is like we also know that na, since P is a probability function, then we know that probability of the whole space comes out to be 1. So that means what? The probability of A union A complement comes out to be 1. Simple. Okay. This is the simplest one. I hope that's clear. These are property, and with the help of these two properties, it will directly write the probability of A union A complement. Okay. What is the probability of A intersection A complement? Can anyone say?
0.
How? We know that na, in set theory. In set theory, we know that na, A intersection A complement comes out to be 0, sorry, 5. Okay. So the probability of 5 we have already defined na, comes out to be 0. In probability function, we define probability of null space comes out to be 0. So that means what? Probability of A intersection A complement comes out to be 0. Simple. Okay. The next question is like suppose two fair dice are thrown. And let E denote the event that the sum of the dice is 5 and F denote, let me write the question and then we will discuss. And F denotes the event that the first die equals 3. Calculate probability of E intersection F. Okay. What we are given, we perform a random experiment in which we roll two dice simultaneously. Okay. Two fair dice are thrown simultaneously, and we define the event E as the sum of the die is 5, and event F, the first die equals 3. Now we need to calculate the probability of the E intersection F. Okay, so that means what is the probability that both the event occurs simultaneously? Intersection comes equals and if union is there, either A or B or both. Okay, so these are actually just the same concept used in the set theory. We will use the set theory concept in probability theory. Okay, so what we are given here, since we are given two dice now, so the sample space, can anyone tell me how many elements are there in sample space and what are the layout? Anyone?
36.
Yes, 36 is there because when we roll a die, the possible outcomes are total 6 possible outcomes is there. So it's 6 to the power 2 comes out to be 36. Okay. And it is ordered pair form. The first die contain 1, the second contain 1. First one, second 2. First one, second 3. Let me write the whole so that we can create some more question just here only instantly. Okay. 1 3, then 1 4, then 1 5, then 1 6, then obviously it's 2 1. It's total 36 is there. Then it's 2 2, then it's 2 3, then it's 2 4, then it's 2 5, then it's 2 6. Okay, it's quite laborious. Na? So I'll try to skip this. Then it's 6 1, it's 6 2, it's 6 3, it's 6 4, it's 6 5, and the last is 6 6. Okay, so we have total number of elements in this set is 36. Up to this point, it's okay. Okay, we roll two dice simultaneously, and the sample space contain these kind of elements. Okay, ordered pair kind of elements, and the total elements possible in the sample space is 36. Now, event E. Event E is what? Sum is 5. No? Sum is 5. Okay. So let's write this event T in roster form. Okay. So how the sum comes out to be 5? So it's 1 and 4 is there. Okay. Then 2 is 3. Then it's 3 and 2. It's 4 and 1. Then there is no other element. Okay. So anyone have any doubt how have I written E in this format? Or do you understand? No? Okay, if anyone have any question, you can directly ask here because I'm not like, okay, yes, you, Pramila Goswami, perhaps. Yes, you have written, right? Okay. Okay, so these are the only four possible uh, cases related to the event E, which is sum equals 5. The event F is also there, which is first die equals 3. So can anyone tell me how can I write in roster form the elements? What are the elements and how many elements are there? First question is how many elements are there? Anyone? There are the answer is 1 by 36. Okay, not okay. The answer is correct, perhaps. How many elements are there in element F? Sorry, in event F. The first, yes, 6 elements are there because the first equals 3 nuns. So it's 3 1, it's 3 2, it's 3 3, it's 3 4, it's 3 5, and it's 3 6. Okay, now the okay F is this. Now it's E intersection F. So obviously you can see clearly it's 3 2's there, is 3 2's there, and there is nothing other elements. So that means what? So that means it's a 3 2. And since there is no conditions applied here, so that means still we have the same sample space. Okay. So the probability of E intersection F is what? Number of elements in E intersection F divided by number of element in the sample space. I have taken here S. Okay. You can take omega. Usually omega or S are taken. Okay. So this is nothing but 1 upon 36. Okay. Very simple question. What I'm going to do is let's create some more questions. I have not written here the same kind of question. One question is there actually. Okay. Suppose suppose the next question is what? Suppose the sum on the dice is 9. Now let event A is sum is 9 and event B is something like first dice was 5. Now, can anyone tell what is the probability of A intersection B? Let's try it first. No? How many elements are there in A? How many elements are there in A? Okay. So the sum is 9. Na? So sum is 9. How can it occur? If we take 1, then 6. Maximum possible number for the second die is 6. So comes out to be 7. So that means we start with 3 actually. It's 3 6. It's 4 5. It's 5 4, and it's 6 3. These are only 4 possibilities when the sum comes out to be 9. Okay, and event B is like first die source 5. Again, it's 5 1, it's 5 2, it's 5 3, it's 5 4, it's 5 5, it's 5 6. Okay, and A intersection B comes out to be like what? Actually, it's nothing but a similar kind of question. We'll create some other question. It's 5 4. Okay. Now, probability of A intersection B comes out to be 1 by 36. What is the probability of A given B? Can anyone solve? What is the probability of A given B? Now, probability of A given B is what? Probability of A intersection B divided by probability of B. So we have calculated probability of A intersection B. Now the probability of B is what? Probability of B is, since we have 1, 2, 3, 4, 5, 6. 6 element is there. So probability of B is number of elements in B upon number of element in S. Make sure, always try to make sure when to use the sample space, the original sample space, and when to use the modified sample space. Okay. So since these are the prior probabilities, so we use the original sample space. Having so this comes out to be 3 upon 36, that is 1 by 6. Now probability of A given B. Now since it is conditional probability, so we use modified. So, or directly we can use the formula. Already we have calculated actually. It's 1 by 36 upon 1 by, it comes out to be 1 by 36 into 6 by 1 comes out to be 1 by 6. Okay. Okay. Now the next question we can construct any question we can construct here. No? What is the, okay, let me define P. Sum is prime. I'm not sure because that's the random question I've generated here. The sum is prime numbers. Okay. Sum is prime and Q is odd. Okay. Now let's solve this question. So let's discuss how many elements are there in this. Anyone have any question up to this point? What are the elements contained in set P? The sum is prime. So 1, 1, 2. Is 2 a prime number? Anyone? Is 2 a prime number? Sorry?
Yes, sir. The 2 is prime number.
2 is prime number. Okay. So it's 2 is prime number. So there is 1 and 1 is also there. No? So that means the element contain 1, 1. Okay. Q has 18 elements. Okay. Okay, let's write na, because I don't know how many elements are there. I'm not going to guess here. So 1, 1 is there. So 1, 2 is there. 1, 3 is not there. 1, 4 is there. 1, 5 is not there. 1, 6 is there. Okay. So now it's 2, 1 is there. 2, 2, 2, 3 is there. 2, 4, no. 2, 5. 2, 6 not there. 3, 2, 3, 4. Okay. Then it's 4, 1, 4, 3, 4, 5, 4, 6. No. 5, 1, no. 5, 2 is there. 5, 3, 5, 4, 5, 5, 5, 6 is there. Because 11 is a prime number actually. Okay. Then it's 6, 1 is there. 6, 3, 6, 4, 6, 5 is there. So actually, let me write here. Na. So prime number is like what? It's 2, 3, 5, 7, 11. These are the all possible cases. Na? So we will collect all those ordered pairs whose sum comes out to be either 2, 3, 5, 7, or 11. So there are possible combination is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 is there. Okay. So number of elements in P comes out to be 15. And for Q obviously it comes out to be 3, 5, 7, 9, 11. Okay. These are the cases because the sum is odd. Sum is odd. That means what? 3, 5, 7, 9, 11. So Q is what? It's 1, 2. It's 1, 4, 1, 6. It's 2, 1. It's 2, 3. It's 2, 5. Okay. So obviously you can directly write. So number of element in Q comes out to be 18. Up to this point, yes, the Admila Goswami, yeah, you said right, Q equal to 18. Number of elements in Q is equal to 18. Okay. So up to this point, it's okay. Now the question, which kind of question we can create? We can create what is the probability, that probability of P given Q. This is the question. What is the probability that it is a prime number when we know that it is an odd number? So it comes out to be like what? Probability of P intersection Q divided by probability of Q. So probability of Q is nothing but 18 upon 36, which is 1 by 2, simple. And probability of, sorry, okay, it's P. Na? Probability of P intersection Q. What is this? Can anyone tell me? What is probability of P intersection Q? Because we have lots of Okay, 1 is not there, 1 2 is there. Okay. Can anyone tell me, or should I write here? If any of the people do not know, then please let me know so that I can write the whole. Okay, let me write now. 2 5. Okay, it's 3 2, 3 4, 3 6. It's 4 1, 4 3, 4 5. Then it's 5 2, 5 4, 5 6. Then it's 6 1, 6 3, 6 5. Okay. Now, what we are going to do is we will find those elements which are common. So 1 1 is not common, 1 2 is common. Okay, 1 4 is common, 1 6 is common, 2 1 is common, 2 3 is common, 2 5 is common, 3 2 is common, 3 4 is common. Okay, it's 4 1, it's 4 3. Are all the elements are common? What? Not sure. It's 5 2, it's 5 6, it's 6 1, it's 6 5. Okay, it's an interesting question then. Which are not common? Let me see. Okay, am I doing something mistake? Can anyone tell me? I think P intersection Q contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 elements is there. Yes, yes. So that means uh, if I'm going to write this, so P intersection Q. Suppose I'm taking the bar, okay, because P intersection Q contains all the elements except 1 1. So its bar contain like what? 1 1. Na? So number of elements in P intersection Q comes out to be 14. So the probability of P intersection Q comes out to be 14 upon 36, 7 upon 80. So probability of P given Q comes out to be 7 upon 18 divided by 1 by 2, which is 7 upon 18. It's 2 by 1. Okay, so probability of P given Q comes out to be 7 upon 9. Okay, so yes, you got the right answer. So this is one of the questions. Okay, we can create any kind of question. What instead of like the same question? Okay, let me know. P term is prime. And it's not Q, but it be R. Sum is even. Can anyone let me know? Then what will be the answer? Anyone? Same. Are you sure? Is there anyone who have the same answer like 7 by 9? You want to say the answer comes out to be 7 by 9?
So 1 by 18?
1 by 18. So one person is saying 1 by 18 and one person is saying 7 by 9. Someone is typing actually. I'm just waiting for her answer. Actually, I thought it's 2 by 9. Na? Because what? The sum either even or odd. Sorry, not even or odd. That means either prime or not something. Okay. Okay, this is your task actually. Okay. The same question, you have to do nothing. Just make again the sum is even, the sum is prime. Okay. So the sum is even, the sum is prime. So what it comes out to be? Sum is even. This comes out to be even, and there is no other elements in there. Okay. So that means P intersection R comes out to be 1. So it's 1. Yes. I think 1 by 18 is the right answer. No? The change हो जाएगा even में only 1 आएगा. Yes, you are right. Even में only 1 आएगा, but our sample space is modified at this point. Okay, because we have already imposed a condition that given R. So the answer will be 1 by 18. So 1 by 18 is the right answer. Okay, so 1 by 18 is the right answer. Okay, now the next question. Let's go for the next question. Okay, let me write the question. Up to this point, any doubt? Anyone have any doubt? Okay, then the next question is, a factory produces 3 different machines. Factory produces 3 different machines, A, B, and C. Let's name them A, B, and the probability of producing machine A. Now, the probability of producing machine A is 0.6. Machine B is 0.1 and machine C is 0.3. Okay. The probability of producing a machine A is 0.6, B is 0.1, and C is 0.3. Then the probability that there is one more information, the probability that the machines A, B, and C will be defective. Are 0.015, 0.01, and 0.02 respectively. Now, what is the probability that a randomly chosen machine is defective? What is the probability that a randomly chosen machine is defective? Okay. So the question is simple, na? We have 3 different machines, A, B, and C. Okay. Is there any question anyone have asked? Okay. So the question is, we have 3 machines. The probability of producing of machine A is 0.6, B is 0.1, and 3 is 0.3. Sorry, C is 0.3. And the probability that the machine A, B, and C will be defective are 0.015, 0.01, and 0.02. Okay. Then what is the probability that the randomly chosen machine is defective? Okay. So it's actually a kind of total of probability. Okay. This question is related to the total of probability. Here we will define the prior information as well as the likelihood event as well. Okay. Let me know. Let me show you. Okay. Wait. So it's like what we are given. Suppose A suppose A is the event which is associated with choosing machine A. So B is choosing machine B. C is machine C. And let me write D. D is a likelihood event which is associated with all these three. Okay, which is nothing but defective machine. Okay, so you are given something probability that A is what 0.6. You are given the probability of machine A is 0.6. Okay, machine A is 0.6. Probability of machine B is 0.1 and probability of machine is 0.3. Okay, this is also we are also given probability that machine A is defective, like probability that it is defective when we are talking about machine A. It comes out to be 0.015. This is the conditional probability. Okay. What we are given? We are given that the probability that the machine A, B, and C will be defective are this. Not all the time. So that the probability that it is defective, given that it is from machine A, is 0.015. Similarly, defective from B is 0.1, 0.9. Defective from C is 0.0. It's 0.01. Yes, 0.1. 0.1 is around 10%. It's 0.02. Okay, these are the information we are given. Now, what we are asking is, what is the probability that when we select a random machine, it will be defective? Okay, so that means we need to find the probability of D. Here, we will use the total of probability. Okay, here we will directly use the total of probability. And what it says? It says like the probability of defective given A into probability of machine A plus the defective will occur either from machine A or machine B or machine C. So that means defective from A into probability of A plus defective from machine B into probability of B plus defective from machine C into probability of C. Okay, now there is nothing, just calculation. D given A is what? 0.015. Probability of A 0.6. Then the next is D given B is what? It's D given B is 0.01 or multiplied with probability of B is 0. Probability of B is it's 0.1 perhaps 0.1 plus probability of D defective given C is what 0.02 multiplied by its 0. Okay, so you need to solve this. It's 0.009 plus 0.001 plus 0.006. So it comes out to be like 0.016. Okay, so probability that a randomly chosen item will be defective is 0.016. That means if you are going to convert this in percentage, then it's around 1.6. Is it simple? Okay, here D, the event D is associated with all the three events. Okay, from machine A, from machine B, from machine C. Okay, so this is kind of likelihood event. Okay, any problem up to this point? Oh, okay. So there is one more question. What we are given, let probability of A equals 0.5, probability of B equals 0.3, find probability of A union B if A and B are independent. Is it okay? Simple question. Now I expect you people answer the question. Let me know, please solve this and let me know the final answer. We are given the probability of A is 0.5, probability of B is this. We need to find probability of A union B. So probability of A union B is what? Probability of A plus probability of B minus probability of A intersection B. We are not given probability of A intersection B. So that means what? We need to first calculate probability of A intersection B. Since A and B are independent events. Okay, so that means what? Probability of A intersection B is probability of A into probability of B. You know that, no? Because this is if and only if condition for two events to be independent. That means what? It's 0.5 multiplied by 0.3. So probability of A intersection B comes out to be 0.1. So now probability of A union B is what? Probability of A, which is 0.5, plus probability of B, which is 0.3, minus probability of A intersection B, which is 0.15, which comes out to be 0.8 minus 0.15. So probability of A union B comes out to be 0.65. A simple question. Only thing you need to know is the properties. Okay. Okay. Now the next question is, like, it's a good question. A person is selling the umbrellas. We are given a person is selling the umbrellas. The probability that he will sell all the umbrellas, the probability that he will sell all the umbrellas with or without rain. With or without rain are 0.90 and 0.42. That means if there is rain, the probability that he will sell all the umbrellas is 90%. And if there is no rain, then the probability that he will sell all the umbrellas is 0.42. Okay. Now the question is, if the probability that it will rain is this. Now we are given if the probability that it will rain is 0.45. That the probability that it will run is 0.45. That is 45% of the time that it will, the chances that ran. Then determine the probability that he will sell all his umbrellas. Okay, so we need to find the probability that he will sell all the umbrellas. See, we have two conditions. He will sell all the umbrellas in rainy season or in with rain or without rain. Okay, with rain 90% of the time he will sell, and without rain 42% of the time he will sell. Okay, now the probability that it will rain is 45%. So the probability that it will not rain is 55%. So we need to like accumulate all these information and find out what is the probability that he will sell all his umbrellas. Okay, the question is clear. It's simple. Let's solve this. Anyone have any doubt? Then please let me know. See, first of all, you need to define the random variable, the events actually. You need to define the events. Without those, you will get stuck. So what we are going to see, we have only two kind of thing. Either it will rain or it will not rain. Okay. And the next is either he will sell the umbrellas or he will not sell the umbrellas. All umbrellas. Okay. So let's define here R. That is, it will rain. Okay. So obviously it's R complement that does not rain. And let us define S. Sell all his umbrellas. Okay. So these are the three events we have defined. Okay. So what we are given, the probability that it will rain is actually 45%. You can see, na? If the probability that it will rain is 45, so it is 0.45. So that means what? Probability that it will not rain is what? 1 minus probability that it will rain, which is 1 minus 0.45, which is 0.55. Okay, that's very clear, very simple. Now we have some more information. The probability that he will sell all his umbrella when it's raining. See, he will sell with or without. With rain, he will sell all his umbrella with 90% probability. That is, it comes out to be 90%. And probability that he will sell all his umbrella when there is no rain is 0.42. These are the information we are given. Now again, the similar question, we need to find the probability that he will sell all his umbrella. Okay, so there are two conditions. He will sell all his umbrella with rain, without rain. So probability that with rain, probability that sell with rain plus probability without rain into probability sell without rain. Okay, in these two conditions, he is able to sell all his umbrellas. So it's like probability R. So it comes out to be 0.45 multiplied by 0.9 plus 0.55 multiplied 0.42. Obviously, that's nothing. This comes out to be 0.405 plus it comes out to be 0.231. So probability that he will sell all his umbrella is yes. Your answer is correct, which is 0.636. Yes, 0.636. The answer is correct. So yes, that's a simple question. Now we have one more question related to Bayes theorem. Okay, the last question related to Bayes theorem. We are given three boxes. Okay, we are given three boxes. Box one contains three red and two white balls. Okay, box two contains four red, sorry, two red and five white balls. And box three contains four red and four white balls. Okay. Now one box is selected at random. One box is selected at random and two balls are drawn. And two balls are drawn without replacement. Okay. If both balls are red, we are given a condition like if we are given an information if both balls are red, then we need to find the probability that they came from box one. They came box one. Okay. The question is simple. We are given three boxes. Box one contains three red and two white balls. Box two contains two red and five white balls. And box three contains four red and four white balls. Okay. One box is selected randomly. So see here, it's random word is there actually. Okay, one box is selected at random and two balls are drawn without replacement. So without replacement is also one of the things we need to focus. If both balls are red, then find the probability that come from box one. Okay, very simple question, straightforward. The first thing, at random. Here, at random means what? Since we are not given the probability related to choosing box one, box two, and box three. Okay. So in that scenario, it is random. So it's random. That implies it has the equal probability of choosing. Okay. The equal probability of choosing. That is probability of selecting box one is equal to probability of selection box two is equal to probability of selecting box 3, which is nothing but 1 by 3. Okay, so that the sum can be 1. Now, without replacement is there. So without replacement is means when we draw one ball, the sample space, the overall the population or the number of elements in the sample is reduced by 1. Okay, so one by one, you take two balls, first one ball and then the another ball. So that means for the first case, we have a fixed number of balls and out of those fixed number of red balls is there. And at the second step, when we draw one ball, we modify our total number of balls minus one. Okay. Then the second ball and then solve the question. So this is the concept. Okay. So let's start. Anyone have any doubt? Then may ask or just try to solve by yourself as well. So like what? Suppose it's B1, like box 1 is selected. Okay. B2, it's box 2 is selected, B3 box 3 is selected. Okay, so these are the events we have defined. With these, we also need to define one more event. Let's define it with R because we need to withdraw 2 balls. No? So both the balls are red. Okay? We need to like withdraw 2 balls. No? Draw 2 balls and both the balls are red. So what we need to find is if both the balls are red, find the probability that it comes from box 1. So that means we need to find what we are given. We are given the both balls are red. It is given probability both balls are red and it comes from box 1. So that is we need to calculate the probability B1 given R. Okay. So we need to calculate this. Just a second. Okay. So what we know that probability of B1 is 1 by 3, which is probability of B2, which is probability of B3, because we do not explicitly given any information of selecting boxes. So here random is there, the word random. So that means both have the equal, all the three have the equal probability of selecting boxes. So that is 1 by 3 is there. Also, we are also given probability of red ball when box 1 is selected. What is the probability of getting 2 red balls, not 1, because R is both the balls are red. We need to withdraw 1 ball and then again 1 ball. So 2 balls simultaneously, 1 by 1, without replacements. So probability of selecting 2 red balls from box 1 is what? So box 1 contain 3 red and 2 white. Okay, so total number of ball is 5. Out of those 5 balls, 3 are red. So first choose 1 ball. So the probability of selecting 1 red ball is 3 by 5. Then, since without replacement experiment has been done, okay, so that means when we select 1 red ball, the number of red ball comes out becomes 2. Okay, and the total number of balls in the box 1 reduces from 5 to 4. So it comes out to be this, which after solving is 3 by 10. Okay, so this is the probability that 2 red ball is selected or drawn from box 1. Is it okay up to this point? Similarly, probability of selecting 2 red balls from box 2. Okay, probability of selecting 2 red balls from box 2 is R given B2. So B2 contains 2 red ball and 5 white balls. So total number of ball is 7. Out of this 2 red balls is there. Okay, so its first ball is selected with the probability 2 by 7. Then since it is without replacement, 1 ball is reduced so from 2 to 1 and 1 ball is reduced from the sample as well. So it is 6. It comes out to be 1 by 21. Okay. Now probability of selecting 2 red balls from box 3 is box 3 contain 4 red balls and 4 white balls. So total number of ball is 8, out of which 4 are red. So it's 4 by 8. Then 1 is reduced. It's 3 by 7. So it comes out to be 3 by 14. Okay. So these are the probability of selecting 2 red balls from box 1, 2, and 3 respectively. Okay. Now we need to calculate what? We need to calculate probability of B1 given R. This is nothing, just probability of B1 intersection R divided by probability of R. Okay. which can also be written in like using the Bayes theorem. Okay, this is the conditional formula. This can also be written like what? Probability of R given B1 into probability of B1 divided by probability of R. Okay. So the denominator term probability of R is evaluated with the help of total law of probability, and the numerator term probability of R given B1 into probability of B1 is using multiplication rule. Okay. So let's start. We already have the probability of R given B1 and probability of B1 is there. We need to calculate probability of R first. Now probability of R, red balls. Okay. So probability of getting red balls is what? Probability of red balls is, suppose we choose box 1, then probability of R given B1. Okay. Plus probability of box 2, probability of R given box 2. Similarly, probability of selecting box 3 into probability of R given box 3. Okay. These are the all three cases when we choose two red balls. So probability of B1 is 1 by 3 into probability of R given B1 is what? R given B1 is 3 by 10. Okay. Plus probability of B2 is 1 by 3. R given B2 is 1 by 21. Plus B3 is 1 by 3. R given B3 is 3 by 14. Okay. So obviously it comes out to be 1 by 10 plus it's 1 by 63 plus it's 1 by 14. You need to just add these numbers. So probability that 3 red ball is chosen. Only the condition is, there is no condition actually. The probability that you select a ball randomly, sorry, you select a box randomly, and out of those box, you draw two balls one by one without replacement, and both of the ball must be equal to red, have the probability 59 upon 315, which is less than 20% actually. If you solve this, you will find that there are very less chance, that less than 20% chance that you select a box randomly, and out of those box you select a, you draw two balls one by one without replacement, and both the balls are red. Okay, having 20% chance. Now our main question is, these balls come from the box 1 is probability that R given B1. So what is the probability that R given B1 is 3 by 10. It's 3 by 10 multiplied by probability of B1. It's nothing but 1 by 3. Probability of R, it's 59 upon 315. Okay, it's simple now. That's 1 by 10 multiplied by 315 divided by 59. Obviously, so probability that B1 given R comes out to be 63 upon 118. Okay. So this is the probability. Okay. This is the probability that the two balls are selected at random and both the balls are red from box 1 is 63 upon 118, which is approximately 51-52%. Okay. So up to this point, anyone have any doubt how we have solved these questions and all? Anyone? Okay. So if there is no question, then I think I'm done with all the questions actually here. Okay. If people have any doubt, any other thing you want to ask related to the course and the questions and all, you may ask here. If not, then we can conclude our session here. Manish typing. Okay. The PDF. Okay. Yeah, sure. The PDF will be available. Okay. Perhaps you people will get a link from the NPTEL team. Okay. From there, maybe they will share some link with you. Okay, from there you are able to access the recording of this lecture as well as the PDF, this PDF as well. But in case you are not able to get from there, you can do one thing. Okay, this is the YouTube channel actually. Okay, this is the YouTube channel. Okay, this recording will be available by tonight or by the next morning. Okay, this whole recording will be there. Okay, the raw recording. Okay, I'm not going to like modify or edit anything here. Okay, this will be on this YouTube channel, and you may find this PDF link as well. Okay, you may find this PDF link as well. There is one drive actually. I've created one drive, and in that drive, I will upload all the PDFs from this week to the last week. Okay. You may the drive link you may follow actually from anywhere. No? You may follow like from LinkedIn. This is my LinkedIn. From there, you may find my web channel, and everything is like connected. Okay. From any place, if you are connected there, then you will find. Okay. And if not, then I will share. I will try to like in description I will write the Google Drive link. Okay, and from those Google Drive link you will find this video. Okay, any other question? Okay, thank you. Anyone have any other question? Okay, then if no, so let's conclude our session here. Okay, then thank you everyone. You people may leave. Okay, thank you very much. Let me first stop the recording.